Alrighty, here we go with 6.4, vectors and dot products. So you probably haven't ever heard of the word dot product before, which makes sense because it is a operation to two different vectors together, which you wouldn't have worked with unless you were working with vectors before. So that's mainly where our focus is going to lie today. Dot products are extremely important to finding the angle between two vectors and determining whether two vectors are orthogonal or not. And that'll be another vocab word we're going to look at today. So far we've been looking at vector operations like addition and multiplication by a scalar, which are all things that when you do them, you still get a vector. Dot product is different in the way that when you do this operation, it yields a number, a scalar, rather than another new vector. Alright, and we have a whole bunch of different properties of dot products, which again are a lot similar to properties of regular numbers. Like, if you multiply something by another one, it's the same thing as the first by the second. Multiplication by 0 is 0. The dot of two vectors which are the same, it's just their magnitude squared. But the more important definition is up top here, which is how do I actually compute a dot product? And the operation that it is to say if I have two vectors u and v which are dotting, I am going to multiply their first two components, and then I'm going to add that to the multiplication of their second components. So it's going to be this one times this one plus this one times this one. So it can get a little confusing if you're not sure if you're multiplying the correct numbers together, but in general the operation isn't too bad. So what I want to do here is to try and just calculate some pretty simple dot products. So I have u is -1, 3. I have v is 2, -4, and I have w is 1, -2. And the first thing that I want to do is u dot v, which is then multiplying w. So like I said before, u dot v, when I have the dot product of two different vectors, what I should get is a scalar, or just a number. So I'm going to get a number here, and that number is going to multiply the vector w. So my end result should still be a vector. So let's see what we get here. U dot v. That's going to be -1, 3. A vector, which is dotting 2, -4. And when I compute the dot product, what I'm going to do is multiply the first two terms together and multiply the second two terms together. So -1 times 2, and that's going to get added to 3 times -4. So -1 times 2 is simply a -2, and I'm going to add that to 3 times -4, which is -12. So when I add all that together, I get -14. That's the dot product of just u and v. Now this -14 needs to now multiply the vector w. So that's going to be -14 times the vector w, which is 1, -2. And when I multiply a scalar by a vector, I simply distribute. -14 times 1 is -14, and -14 times -2 is 28. That just went crazy. And that is my resultant vector, which is the dot product of u and v, times the vector w. Now let's look at part b. B says that I want u dotted with 2v. Okay, so first I need to figure out what 2v is. So v is 2, -4. And that means that 2v would simply be multiplying this vector by a 2. 2 times 2 is 4, and 2 times -4 is -8. So this is my resultant vector from the scalar multiplication. And what I want to do is dot this with the vector u. So the vector u is -1, -1, 3. So when I dot things together, I multiply its first two components, and I add that to the multiplication of its second two components. So I'm going to multiply the first two. I get -4. And when I multiply my second two components, I get negative 8 times 3, which is going to be negative 24. And when I add these two things together, I get negative 28. So I get a scalar here, right? I have the vector u and the vector 2v, and when I dot them together, what I get is a resultant scalar number. So this is not a vector, it's just a number. And let's look at our last one, the magnitude of u. Well, that actually seems simple. I think this is supposed to be the magnitude of u squared, right? Because there's a property on my last page which tells me that the magnitude of a vector squared is actually equal to u dotted with itself. And I think that's what I'm supposed to be doing here. So u dotted with u. That's negative 1 comma 3. That's being dotted with negative 1 comma 3. Now I got to do the same process again. I multiply the first two together, I get a 1, and I add that to multiplying the second two together, which is 3 times 3, which is 9. So I'm looking and I'm getting a value of 10, the dot product of u and u. Or I could have, again, just taken its magnitude and squared that number. Fantastic. Now let's look at the angle between two non-zero vectors. This is where dot product becomes very important. Okay, because within the formula of finding the angle between two non-zero vectors, the dot product plays an integral role. It's actually a secondary definition of the dot product. All right, if I rewrite this formula here, I get that u dotted with v equals the magnitude of u times the magnitude of v times the cosine of theta. So that's a secondary definition of the dot product, as opposed to multiplying the first two components, adding it to multiplying the second two components. And we'll be able to actually go through a proof of this later on in the chapter. But this is how we find the angle between two vectors. I take the dot product of the two vectors, I take their magnitudes and I multiply them, and what I'm going to have is the cosine of theta equals this number on this side, right? Because the dot product yields a number, the magnitudes are both numbers, so I'll get a ratio over here, and that'll tell me, once I find the inverse cosine, what the angle is. So let's take a look at this. Finding the angle between 4,3 and 3,5. Well, what that means to me is that I have to find the dot product between 4,3 and 3,5, and then place that over the magnitude of 4,3 and the magnitude of 3,5. So let's start filling in some numbers for these things. The dot product on the top there is going to be 4 times 3 plus 3 times 5, and what that's going to come out to is a 27. And on the bottom, the magnitude of the first and the magnitude of the second. Let's see, this is going to be 4 squared and 3 squared, and this is going to be 3 squared and 5 squared. Multiply all that together, what I'm going to end up with is 5 square roots of 34 when it's all said and done. Alrighty, so now that I have this, this implies to me that the cosine of theta equals this ratio, 27 over 5 square roots of 34. Now, I don't have a place on my unit circle that tells me where this is. So what I'm going to have to do is the inverse cosine of 27 over 5 roots 34, and that will give me my theta value. And what it turns out when I plug this in is it's about 22.2 degrees. Very good. The important part of this is to be able to compute the dot product up here, and then, you know, we've been doing magnitudes for a while, and multiplying those together, that shouldn't be too difficult. Now, an interesting definition here is using the dot product to figure out if things are what's called orthogonal. Now, orthogonal just means perpendicular. Okay, it's just a kind of like a more fancy word for it. Now, when the dot product equals 0, this means that two things are orthogonal. Why does that happen? When I look at the definition of the angle between two vectors, if the dot product is 0, that turns this entire side into a 0, which means I'm looking for the inverse cosine of 0. Right? And what that's going to be is where on the unit circle the cosine equals 0, which is at a 90-degree angle. So whenever that dot product equals 0, we can immediately say, I know these two things are perpendicular. They're orthogonal to each other. So when I go to check to see if two things are orthogonal or not, like vector u and vector v here, all that I have to do is take their dot product. If I find that it comes out to a number, I know they're not orthogonal. If I find that it comes out to a 0, I know that they are. So what do I do here? 2 times 6 plus negative 3 times 4. 2 times 6 is 12. Negative 3 times 4 is negative 12. And when I add those two things together, I get 0. This means these two vectors are, in fact, orthogonal. Now let's talk about finding vector components.
Who told you you can eat my cookies?
So when we're finding vector components, whether it's at an acute angle or an obtuse angle, what we want to do is try and create two different orthogonal vectors, one W1 and one that is W2. And what's going to happen is when you add together W1 and W2, the resultant would be your original vector u. So the first W1 is what we call a projection of u onto the vector v. So it's a projection in the direction of standard position for that vector. So we have our first W1, which is the projection of u onto v, and then our W2 will simply be orthogonal to that. So here's what we have to do in order to find the projection. We take the projection of u onto v is essentially the dot product of u and v together over the magnitude of v squared times the vector v. Now the notation of projection is very important to recognize. The projection of u onto v is written with the large letter u and the small letter v right next to it. Alright, so that's important to say. So anyway, it's the dot product of u and v over the magnitude of v times, again, the vector v.
You're killing me, Smalls.
Afterwards. So your solution to this whole thing will be a vector solution. So here, let's try and find the projection of u, 3, negative 5, onto v, 6, 2. So it's the projection of u onto v. Alright, so what we first have to do is find the dot product of u and v, because that's the first thing right there in the top of the projection. Alrighty, so what we do is we take 3 times 6, and then we take negative 5 times 2, and we add those two things together, and what we're going to get there is an 8. As for the magnitude of v squared, I essentially am doing some sort of Pythagorean theorem or distance formula. So 6 squared and 2 squared, and then I'm going to go ahead and add those two things together. And I would normally take the square root, but since I'm squaring it anyway, it's a 40. And then I multiply that by the vector v, 6, 2. So what I have here is the fraction 8 over 40, which is then going to be distributed into both the 6 and to the 2, the vector for 6, 2. And when I distribute 8 over 40 times 6, as I get 6 over 5. When I distribute 8 over 40 to the 2, I get 2 over 5. So that is my projection vector right there, 6 over 5, comma, 2 over 5. Now, there's more to this. I don't want to just find the projection. I also want to write the u, the original vector, as the sum of two orthogonal vectors. Now, what I said before was that finding this first projection is one of the orthogonal vectors. So now all I have to do is say that my second orthogonal vector will be u minus the first. And that's because W1 and W2, when they're added together, their resultant is u. So by just switching around the equation, making a subtraction, I can make this work. So what I get is the original vector u, 3 comma negative 5, minus my new projection vector. And what this is going to give me is my other vector, which when added to my projection would have produced as a resultant my u vector. So now it's just simple vector subtraction. When I do 3 minus the 6 over 5, I get 9 over 5. When I do negative 5 minus the 2 over 5, I get a negative 27 over 5. So here I have my two vectors, 6 over 5, 2 over 5 as one of them. That's my projection of u onto v. And then I also have my 9 over 5 and my negative 27 over 5, which is my second orthogonal vector. These two are orthogonal to each other, and when I add them together, their resultant should be u, which, if I add 6 over 5 to 9 over 5, I get 3. When I add the 2 over 5 to negative 27 over 5, I get negative 5. So perfect. It works out. And that's a great way to check to make sure that you've got them both right. Now let's talk about work. All right, the work done by a constant force F acting along a line of motion is given by this. It's basically just the magnitude of force times the distance. However, when we're dealing with, pulling something in a direction, generally you have a force going upward, or it's just some angle upward. And really the force in the direction is that projection in the horizontal direction. So our formula becomes a little bit more complicated. It's really the force from the projection, the magnitude of that force, times the distance that you're traveling. So it's still the same basic idea, force times distance, but that force becomes a bit more complicated because it's not the force that you're pulling upward with, it's instead the projection force. All right, so this can be written in a couple different ways. One where you have actually projection times the distance, one where it's the cosine times the force times the distance, and another where it's the dot product of the force vector and the distance itself. So here are the two basic forms that we want to look at: the magnitude of the projection of the force times the magnitude of the distance, and the dot product of the force vector and the distance vector. So let's look at this one. To close a barn sliding door, a person pulls on a rope with a constant force of 50 pounds at a constant angle of 60 degrees, as shown in this figure. Now, the actual force that's needed to close the door is that projection vector going directly horizontal, not the one that's pulling at that angle. So we have a little bit of work to do in order to find that work. So work equals, in this case, the magnitude of that projection vector, the projection of the force in the direction of PQ, times the magnitude of PQ, the actual distance that work is being done. Now, the projection vector, in our case, the magnitude of the projection F, can be rewritten as the cosine of the 60-degree angle that's being pulled at times the actual magnitude of the force that's happening. That's one of those other ways of writing it from before. And then that times the magnitude of the vector PQ, which is the distance. So cosine of 60, 1/2. The magnitude of the force, they said it was 50 pounds of force. And the magnitude of the PQ vector, 12 feet. So really all we have to do is multiply 12 by 50 by 1/2, and you find that your force is 300 foot-pounds. And that's as simple as it is. Alrighty, take a look at your assigned problems, do all those, make sure you're good with them, and I will see you guys in class next time. Fare thee well.
Oh my God!